Hi, my name is Alena Bowman, and I am part of the education team at the MSU Museum. Today, we're going to be continuing with our virtual webinar series. We're using an online version of our Science on a Sphere exhibit to talk about currents. If you haven't already done so, I encourage you to download the SMS Explorer mobile app in the App Store of your Apple or Android device. It should look something like this. All right, I'll load my app. Might take a minute. So the SMS Explorer app is made by the same people who gave us our Science on a Sphere exhibit, NOAA, the National Oceanic Atmospheric Administration. So we have a lot of data sets on here. Most of them we have on our actual Sphere exhibit. We have some on our Sphere exhibit that we don't have in the app. Once it loads, so on the left side, you see that we have a panel where you can choose the data set that you want to load. So I'll be talking us through a couple of those data sets. And then in the bottom right-hand corner are a couple buttons. I like to use the 2D, 3D button. It changes it from this 3D view to this 2D view. And sometimes it's just easier to see a pattern in one of those views. It's easier in one view than the other. We also have the overlays button, so you can turn on country borders, country labels, grid lines, anything like that. Just something additional to add to your screen. All right, feel free to follow along and get started with our program. The first data set we're going to look at is under air. So the top here, we go to the categories and air, and then it's called WIND's GEOS 5 model. So all the way down at the bottom. You might notice that a few of these data sets have been used in our previous virtual webinars, but hopefully it will give you some new information, a new way to look at it, and a new way to relate to other data sets. So currents are the way water or air moves. If you ever watched a river of rain race down a street curb, you've seen a small current. There are large currents, though, all over the globe that move water through the oceans and affect climates and therefore the weather. And wind currents are actually a big part of what creates ocean currents. So if you look at this view of the wind currents, you can see they're swirling all over the earth. Some of them are stronger than others. Yeah. So let's compare this to some sea surface currents. If we go to water category and then scroll to sea surface currents and temperature and pull that up. Give it a second. All right, so this is again in 2D, the 2D view. So you can see all of the patterns across the world at once. It looks kind of similar to the way the winds are moving, right? So I can let this data set run for a bit while I explain how these ocean currents form. This is actually my favorite data set. I think it's super cool to see on the actual Sphere exhibit, but also just in the app because of all the colors that represent the different temperatures and the way that the currents are swirling all over the earth. So as the wind blows across the surface of the ocean, it moves the surface waters. So thus the sea surface currents generally look like the wind currents. However, the deeper ocean currents actually tend to rotate in the opposite direction because of something called the Coriolis effect. The Coriolis effect occurs because the Earth rotates. It isn't just staying in one place as it goes around the Earth, it's spinning. So the ocean and wind currents curve as they move away from the equator. They don't just go straight up and down. So when surface water moves because of the wind, it drags the deeper layers of water with it. But each deeper layer moves more slowly until the movement stops at a certain depth. But because of the Coriolis effect, the water doesn't actually stop, it keeps moving. As it goes to the right in the northern hemisphere and to the left in the southern hemisphere. So because those deeper layers of water move more slowly than the shallower layers, they tend to spiral around because they're kind of moving more slowly and then they get affected by the Coriolis effect. And they end up moving in the opposite direction to the surface current. So the Coriolis effect also affects wind currents. So basically after the air is warmed by the sun at the equator, it moves up into the right in the northern hemisphere and down into the left in the southern hemisphere. So the reason this movement of water and air occurs at all is because the water or air wants to be at the same temperature. So the warmed air or water will go where it can mix with cooler water, and this helps regulate our climates on land, which Nick talked about in his climate webinar last week. So you can see that all of these currents are swirling and mixing, and then the temperatures are changing. The currents are bringing different temperatures with them to different parts of the world. Yeah, pretty cool. All right, so without ocean currents, our world would be super hot at the equator and super cold at the poles. So you might remember this data set from an earlier webinar. We go to land, the land category, and then scroll to the land surface temperature. They're alphabetical order here. Land surface temperature. Yeah, so you can see that it's already warm at the equator all year round. Imagine what that would look like without ocean currents. None of this mixing would happen. We would have hot and cold temperatures all over the place, and our climates would be a lot more extreme. Let's go back to my slides. All right, so the El Nino Southern Oscillation is something, it's a cycle that involves both the ocean and the wind currents that we just talked about. That essentially changes the climate in the affected regions. It has an especially large impact along the Pacific coast of the Americas and in the southern US. So this next video, about 2 minutes, will explain how El Nino and its counterpart La Nina affect global weather patterns through changing wind and ocean movements.
Warmer or colder than average ocean temperatures in one part of the world can influence weather around the globe. Boggles the mind, right? Here's how it works. During normal conditions, trade winds, which blow from east to west, push warm surface waters towards Asia, piling it up in the western Pacific. In some years, though, the trade winds weaken. The warm surface water moves eastward and reduces upwelling of cold water off the coast of South America. Climatologists call this El Nino. Its climate impacts show up mostly in the wintertime over North America. The warmer ocean fuels an intensification and southward shift of the jet stream. This brings flooding to the southern United States and warmer, drier conditions over parts of the Pacific Northwest, northern US, and Canada. But eventually, those trade winds pick up again and sometimes become even stronger than normal. When that happens, they blow the warm water back into the western Pacific and restart the upwelling of cool water towards the surface in the eastern Pacific. These strong trade winds are a signature of what is called La Nina, unusually cold conditions in the tropical Pacific that displace the jet stream northward. La Nina can lead to drought in the southern U.S. and cooler temperatures, heavy rains, and flooding in the Pacific Northwest. El Nino and La Nina together are part of a cycle that influences extreme weather and can impact food production, water supply, and even human health, not just in the U.S., but in many parts of the globe.
All right, so that video included, that video kind of showed us that the interactions between those trade winds and the upwelling can create this huge weather pattern that affects us and our patterns all over the world, those climate patterns. One of those severe weather events that is influenced by El Nino is the hurricane. I'll bring up another video that explains the process of how hurricanes are formed, but essentially it's when the warm oceans around the equator interact with changing air pressure. About 2 minutes.
Hurricanes are very large and intense storms. But where do these giant storms come from? A hurricane starts with the warm water found near the equator. Hurricanes typically only form in tropical regions where the ocean is at least 80 degrees Fahrenheit. These warm waters evaporate, creating warm, moist air which acts as fuel for the storm. Wind is also needed for a hurricane to form. Many hurricanes in the United States are caused by winds blowing across the Atlantic Ocean from Africa. This wind causes even more of the warm water to evaporate into the air. The warm, moist air then rises high into the atmosphere, where it begins to cool. Way up there, the water vapor condenses back into liquid water droplets. water droplets in the atmosphere form clouds, including big, stormy cumulonimbus clouds. As the warm air continues rising upward, the winds begin blowing in a circular pattern around a center. The spiraling winds gather up a cluster of big thunderstorm clouds. Once the spinning winds reach 74 miles per hour, the storm has officially become a hurricane. Hurricanes are huge. They can be 10 miles high and over 1,000 miles across. Once a hurricane hits land, it runs out of warm, moist air and its winds begin to weaken. But the storm can still cause lots of damage to communities near the coast. Thankfully, we have weather satellites that are constantly monitoring the conditions down here on Earth. The GOES are a series of weather satellites scan the hemisphere every 10 minutes and the U.S. every 5 minutes, keeping an eye on conditions that might cause a hurricane to form. Once a hurricane forms, the satellites can help predict the storm's intensity and track it minute by minute. This information allows meteorologists to deliver early warnings and help people stay safe. Find out more about Earth weather at NOAA's SciJinx.
So these last two videos were made by NOAA, the same people who make the app and the exhibit. And that last video included some information about the data that NOAA collects using weather satellites. So that data can go into creating satellites like the one, or creating data sets like the one we're going to bring up now. All right, so if we go to the water category, and then scroll to hurricane tracks, cumulative, yeah. So this data set isn't supposed to move or anything, but it does show the severity of different hurricanes and then their paths. If we look at the whole world version, well, first you can see that Michigan doesn't get a whole lot of hurricanes. The storms that do get up there are usually tropical depression or tropical storms by then. And that's because, like the video said, those storms run out of steam once they hit the coast. Let's look at the 3D or 2D version. So you can see that all of the hurricanes are starting at the equator. And then you can also see that the storms curve along certain paths. This is due to the rotation of the Earth and the Coriolis effect that we talked about earlier. The hurricanes, like the wind currents, tend to go up and to the right in the northern hemisphere and down and to the left in the southern hemisphere. So El Nino and La Nina also lead to extreme weather events like droughts and large floods. The next data set we can look at is under land, and it's called Fires Annual Cumulative. All right. So it might be kind of hard to see on my screen, but hopefully you can see it in better resolution on your own screen. We can see that some areas are just more prone to fire than others. Some of these fires are human caused, but a lot of times in drought areas, fires can occur naturally. So if La Nina causes a drought, then it might increase the, or if the El Nino Southern Oscillation causes a drought, then it might affect the fire patterns in this area of the world, maybe. Also, keep in mind that in addition to needing dry, hot weather, fires need something to burn. So the Sahara Desert in northern Africa might not have quite as many fires as you'd expect given the land temperature that we saw earlier. South America might have a few more because it's got a lot of trees. All right, so the other data set that we can look at for these extreme weather conditions is flood events. So it should be right underneath floods with rivers. 2000 to 2009. So again, this one doesn't change, it's just cumulative events. We do have, we can access real-time data about events like these on the real sphere when the ad exhibit is open, when the museum is open. But in this data set, you can at least see that flooding is generally common around coastal areas and rivers, especially in the US here. So those areas would be very susceptible to flooding during the El Nino Southern Oscillation, especially in the southern US. So another way that ocean currents are created other than by winds and the Coriolis effect is through the gravitational attraction of the sun and the moon, but mostly the moon, on Earth's ocean. So we can bring up a data set that shows us the moon just for fun. Go to space, and then moon. Moon topography might also be pretty cool to look at. It's more colorful, certainly. So the moon and the gravity and that interaction on Earth creates tidal currents in the oceans and on the coasts. These currents are more predictable than the currents created by the winds, and they're used to figure out when the best time is to take out a boat out onto the water, which is important for fishermen and people on larger barges, shipping companies. So back to the slides. So wind and ocean currents affect weather and climate, but they also affect other parts of our daily lives. People use what we know about currents to navigate boats that are shipping goods all over the world, like in this top right picture, or top left picture, sorry. The trade winds that were mentioned in the El Nino video, they're called that because that's what blew trade ships that were shipping goods and services across the oceans. That's what those ships were using, those trade winds. People also use currents to look for people or things that might get lost at sea. So coastal rip currents in the bottom left photo or graphic can be dangerous for swimmers, so knowing about those currents could save someone's life. Fishermen can also use their knowledge of currents to maximize their catch for the day, like the people in the right photo here. On the other hand, though, ocean and wind currents have the potential to move harmful pollutants all over the world. So you can see here, hazmat teams can track currents to figure out how best it is to clean up an oil spill, like the one on the left here, before it spreads too far in the ocean. Ocean currents working together have also created gyres, where giant patches of garbage have formed, like the North Pacific Gyre, which created the giant Pacific garbage patch that you have probably heard of. The tiny pieces of plastics called microplastics have been found all over the oceans, even in Antarctica. An interesting data set to bring up real quick is, let's go back to the app under air, the air category. And it's atmospheric chemistry. This data set comes up quite a bit because it's super cool to look at. Let's hope it loads. Yeah. Yeah, so you can see that here we see how air currents blow dust and air pollutants like sulfates to different parts of the world. They don't just stay where they're shot into the air. Yeah. It's a cool data set to look at, but it also reminds us that our actions can affect the whole world, so we should be careful what we put in the air and on the ground. Yeah. Because the wind and ocean currents have the power to move those things around. Let's go back to the slides. There we go. All right. So while the currents have the positive power to regulate our climates and help us with fishing and shipping and bring rain to our land, the power can turn dangerous if we aren't careful. So not littering, or maybe reducing your trash altogether, trying to go zero waste or minimal waste, using your car less, so biking, walking, and advocating for clean sources of energy, renewable energy sources like wind power and solar power that Nick talked about in his climate webinar. And it just so happens that today, March 22nd, happens to be Earth Day. It's a great day to get started doing something to help the Earth. You can just Google Earth Day 2020, and you should be able to find some really cool resources and options for activities you can do either now while we're stuck in our homes, or maybe some cleanups that'll be hosted in a few months. If you're looking for something else to do while you're stuck at home and want to see for yourself how currents work, keep watching. Feel free to pause the video or come back to it later. If you don't have the resources on hand, you're also welcome to just watch the demonstration without doing it yourself. So here's the list of what we'll need. We need a flattish bin or pan filled with a couple of inches of warm water, a few drops of food coloring, whatever color you'd like, a couple of rocks or cups if you can't find any rocks, and a bunch of ice cubes. So 6 is probably a good number. Alrighty. Cue the video. Alrighty, so for this activity, we just need a pan, some warm water, some ice cubes, and a few drops of food coloring, and we can understand how ocean currents work. We take a large container like this and fill it with a couple of inches of warm water and some rocks. The warm water represents the oceans of the world, and the rocks represent the continents. Alright, let's see what happens when we add a drop of food coloring. Not a whole lot. It hits the bottom and it just kind of spreads out from there, right? Alright, what happens if I add some ice cubes to the water? Add as many ice cubes as you want. Alright, let me add one more drop of food coloring. Maybe over here. Maybe over here. Alright, let's watch what happens when the discolored water hits the continents and how it moves. So you see it is actually moving in directions now. So in the pan, the cold melted water from the ice cubes is denser than the warm water in the pan. That means that there's more water packed into the same amount of space. So that colder water drops to the bottom of the pan and moves along the bottom until it warms up, and then it rises up to the top again. The same kind of thing happens in the oceans. So like the oceans, like the pan, the oceans of the Earth are not all the same temperature. The North Pole and South Pole are a lot colder. So that cold water drops to the bottom of the oceans and it moves towards the equator until it gets to where all that warmer water is as it warms up. So this creates large-scale deep currents. These currents are responsible for moving large amounts of water from one part of the world to another. Let's see, we've got these little currents moving around here. We kind of just created our own currents in this pan. And they're still moving. Just kind of mixing all together. Alrighty, thanks for sticking around for this activity. I hope you enjoy the program and have a good rest of your day. Before you enjoy the rest of your day, I have one more slide for you guys, and it is this one. If you're feeling generous and would like to support the MSU Museum's educational programs like the virtual webinar that you're watching right now, we'd really appreciate the support. So the link is here, and it should be posted in the comments wherever you're watching the video. All right, thanks for tuning in, and we'll see you next week.